And physiology and yeah, okay. General pathology. Let's get that opened up. Sorry about my laptop fan. I'm trying to get it to run as much as I can because it's so cold in here, and my computer warms up the environment. But anyway, okay. Where were we? Oh, nothing there. Okay, starting off, calcium imbalances. The consequences of calcium imbalances are ATP depletion, leaky gut, right? Not good. Well, not necessarily leaky gut, but pores in the mitochondrion, I guess. It also activates deleterious enzymes, bad enzymes, and it starts apoptosis. Too much calcium in a cell is a bad thing as well. Defects in membrane permeability. It can be caused by a couple things. First thing is reactive oxygen species. Second thing is alterations in phospholipids. And there can be consequences of this. The opening of the MPT pore, plasma membrane damage, or injury to lysosomal membranes. There can also be damage to DNA and proteins, and if the damage is too severe, can't be repaired, then the cell will go through programmed cell death, which is apoptosis. That's what apoptosis is. But cancer can override that because, mutated cells are supposed to go through apoptosis. You're not supposed to have mutations. But cancerous cells are often mutated. And so they mutate and then they keep living because they no longer listen, basically. They don't listen to the thing that tells them to do apoptosis anymore. So, the cells that easily and readily proliferate are called labile cells. And then the cells that can divide if they really need to are called stable cells. The cells that are terminally differentiated and can't divide are permanent cells. Okay, this is reversed from what we learned earlier. Earlier they said the cells that easily and readily proliferate are stable cells, and the cells that can divide if they really need to are labile cells. So that is a little bit backwards, but all right. I'm not sure which one's right then. But the permanent cells are the ones that can't be made new. Heart cells, brain cells, you can't make more of those. That's why you got to protect what you got, or what you have. Reactive oxygen species, also known as free radicals, not good. There's a small amount is generated normally, but your body clears them out via antioxidants. You can also get them by absorbing radiant energy like UV light, X-rays. Bro, what's up, Todd? Reactive oxygen species. It's good to see you again. Yeah, antioxidants, antioxidants scavenge those free radicals and they remove them, basically. But here's an important thing. You don't need antioxidants if you don't have oxidants in the first place. Turn on subs. What does that mean? I've got my subscriptions on. You can, if you're trying to subscribe, you're able to, I think. Well, let me know if it works. I'm not sure if it's not working. Yeah, I don't even know. I didn't even know you could turn that off. I don't think I did anything. I don't think I turned it off. Just go to click on my channel. It should be near the bottom. Click on my channel at the bottom and you'll be able to subscribe to it that way, probably. Or you might have to, or I don't know. You're probably signed in, right? I don't think it's that. Anyway, reactive oxygen species aren't good. Can cause reversible and irreversible cell injury. Oh, okay, you're already subscribed. Yeah, I've done that before. That's happened to me. I've tried to subscribe and it wouldn't work. But your cell's going to swell and there's going to be a fatty change as well. It's called hydropic degeneration. Hydropic degeneration, something like that. Anyway, ATP is getting depleted, so it's not able to control the ATP-dependent sodium-potassium pumps. And then sodium goes in the cell. Where the salt goes, the water follows. So water goes in the cell, and then those cells swell. Not good news, really. There's, again, and this is the reversible kind. It'll swell, but it can unswell too. Hydropic or hydropic degeneration. You can have it in the liver, you can have it in the epidermis. Swelling is an indicator of reversible cell injury. So here's a review. An increased number of cells is termed hyperplasia. An increased size of cells is termed hypertrophy. A decreased size or number of cells is called atrophy. And a change from one cell type to another is called metaplasia. Also, an abnormal cell formation is called dysplasia. A to Z farm, you're weird. Thank you. I'll take that as a compliment. Consider the following. What are reactive oxygen species and where do they come from? Reactive oxygen species are unpaired electron radicals. There's some generated in the mitochondria, but there's also some made from cell injury. How are they removed? How are reactive oxygen species removed? By antioxidants. So if you've got oxidants, antioxidants remove them. An excess of reactive oxidative species, was it? Reactive oxygen species? I'm having a brain fart for some reason. Leads to oxidative stress. Not good. But the main features of reversible cell injury are that the cells are full of water. Okay. Irreversible cell injury it happens once it's past the point of no return. The cell cannot reverse mitochondrial dysfunction, and there's profound disturbances in membrane function. There's two outcomes of that. Either necrosis or apoptosis. And we're going to talk about those right now. So necrosis is usually worse, and apoptosis is more controlled. Necrosis is like more chaotic. For example, here's a very good analogy of necrosis versus apoptosis. Say you went camping. You put up a tent. Now it's time to go home. You're done camping. How are you going to get rid of the tent? Necrosis says you put some dynamite next to it, light the dynamite, go run, and explode the tent. Blow it to smithereens. Apoptosis says you dismantle the tent. That's the difference between necrosis and apoptosis. Some characteristics of necrosis is an enlarged cell size, swelling. The nucleus undergoes fragmentation. The plasma membrane is disrupted, which leads to leakage of cellular contents. And then you often see adjacent inflammation, and it's always pathologic. It's never a good thing. Now, apoptosis has shrunken cells, a condensed and fragmented nucleus, an intact plasma membrane, and mostly intact cellular contents, and no inflammation, and it's often physiologic, but it can be pathologic, which means it can be bad. But most of the time it's not. Most of the time it's programmed. Or intended by the body. Some things that can cause necrosis are hypoxia, ischemia, or direct damage to cell membranes. Happens as a result of ATP depletion, which leads to disruptions of the sodium-potassium pumps. Then mitochondrial dysfunction, calcium influx into the cell, and then reactive oxygen species formation. The cell will lyse, which means it will break up, and it will leak its contents into surrounding tissues, which causes inflammation. Not good. It appears differently grossly, though, which means visibly to the naked eye. You have gangrene, frostbite, right? Those are all forms of necrosis, but they look differently to the visible, visible to the eye. That's what gross means in this context. Histologically, the cell swells, which leads to cell lysis, which again, lyse means to explode or break. And there are changes to the nucleus as well. The nucleus shrinks and condenses, which is called pycnosis. It breaks into components, which is called karyorrhexis. And then it fades away and dissolves, which is called karyolysis. Yes, very, very gross images can sometimes follow discussion of necrosis. Now, talking about apoptosis, it's programmed cell death. It's a lot more organized. The cell shrinks and kind of just gets dismantled often. There's an intrinsic pathway and an extrinsic pathway. It's often physiologic, and there's no inflammation involved. Happens during embryology, like the webbing between an embryo's hands or feet goes away after a while if it's an animal that doesn't have webbed feet, like humans. Sometimes it doesn't happen, right? Some humans have webbed hands. So there's mistakes that can, or there's abnormalities that can occur. But apoptosis also happens during homeostasis, just getting rid of old cells, right? Involution of organs and tissues, I kind of just said that. Or it can happen during changes in or decreased hormone signaling. So if the hormones decrease or change in any way, apoptosis can occur. But there's also some pathologic examples: DNA damage, misfolded proteins, infections, or a host immune response. Autoimmune diseases like lupus, that's an example. Those are some examples of how apoptosis can be bad. Now, the intrinsic pathway versus the extrinsic pathway. Intrinsic is internal injury. Extrinsic is external stimulus. Inside out versus outside in. Okay. There's a bunch of specifics there that we probably don't need to get into. Blah, blah, blah. Yeah. Dismantle a tent or you blow it up. Apoptosis versus not neoplasia. Goodness gracious, I already forgot. Necrosis. Anyway, okay. I think that's it for general pathology. Moving on to physiology. All right. So, previously we talked about micturition and edema. Micturition being urination, and edema being fluid that's not supposed to be there, that's in your tissues, basically. You know, you've got swollen looking tissues. Nasty, nasty pictures. Edema can be intracellular or extracellular. And yes, anyway, moving on. So micturition, there's a 3-step process. There's the glomerular filtration of the urine, tubular reabsorption, and then tubular secretion. There's an equation here that I don't need to share with y'all because it's not going to help y'all much, but there's 4 classes of substances that go through your kidneys. Class A are the ones that are filtered and not reabsorbed, like creatinine, inulin, and uric acid. Class B is filtered, partly reabsorbed substances like sodium ions, chloride ions, bicarbonate. Class C, which is filtered and completely reabsorbed substances like amino acids and glucose. And then Class D, which is filtered and secreted substances like organic acids and bases. Class D substances your body completely gets rid of. Class C your body completely keeps. And then B and A are kind of in between, if that makes sense. I think that was correct. I'm not 100% sure. That's what it made sense to me, though. Okay, water. Your body reabsorbs basically 99% of the water you drink, but it excretes some. Sodium, your body basically reabsorbs 99%, but it excretes some. And it varies. You drink too much water, you're going to pee more water. You eat too much salt, your body's going to excrete more salt out through your urine. Glucose, your body reabsorbs all of it, in the urine at least. And then creatinine, your body doesn't reabsorb any of it, it excretes all of it. Different solutes are cleared at different rates. Inulin is the benchmark, basically. Anything that has a higher clearance rate than inulin is basically also added to urine by the tubular cells. Tubular cells are the cells in your blood, I think, that take it out of circulation and add it to the urine to make sure that it's 100% cleared. A high GFR, glomerular filtration rate, is necessary to remove waste products. 20% of cardiac output is reabsorbed or filtered by the glomerulus. And all of our blood is being filtered about 60 times per day. That's a lot. And that's pretty cool. Again, there's all these equations. If your filtration, okay, there's something called a filtration fraction. It's a decimal. So if your filtration fraction is 0.2, that means that 20% of blank flowing through your kidneys is filtered. So if it's plasma, then 20% of the plasma flowing through your kidneys is filtered. But if the filtration fraction is 0.5, then 50% is filtered. So that's a pretty simple equation. Some things have high molecular weights, though, in your body, like proteins, and they're not as filterable. For example, myoglobin. Your body is only able to filter about 75% of the myoglobin in your blood because it's such a large molecule. Albumin is even larger, and your body barely can filter any of it. It's only able to filter like 0.5% of albumin. Not a lot at all. Yep, filterability. And there's forces that affect filtration. For example, a glomerular hydrostatic pressure of 60 millimeters of mercury and a Bowman's capsule colloid osmotic pressure of 0 millimeters of mercury are favorable to filtration. Meanwhile, a glomerular colloid osmotic pressure of 32 millimeters of mercury and a Bowman's capsule hydrostatic pressure of 18 millimeters of mercury are not favorable for filtration. They are actually the opposite of what you'd want. Not good. Chronic diabetes can injure your glomeruli, and that can really hurt kidney filtration rates. That's pretty much it for January 16th. Other than that, we had a class called Professional Skills. We pretty much just talked about finances and start investing, saving now rather than wait until later, because the sooner you start, the better off you'll be. Yeah, that's pretty much it. So thank you all for watching, and I'll see y'all in the next one.